The next problem I'd like to look at is number 20. It shows a problem that requires a bit more work than the traditional. So you have time a bit. Find the points in the curve where you have a horizontal and a vertical tangent. Well, dy dx, y depends on theta. They should be t, but it's the same thing. E to the cosine of theta times negative the sine of theta. And e to the sine of theta times the cosine of theta with the chain rule. So if I want to do those individually, I would look at where would dy dt equal 0. That would indicate a horizontal tangent. So that would be when negative sine of theta e to the cosine of theta equals 0. Well, either sine of theta equals 0 or e to the cosine of theta equals 0, but that can never happen. Exponentials can never be negative, so it has to be the sine of theta is 0. That happens at an infinite amount of points. That happens when theta equals 0 plus pi k, right? So if I take theta equals 0, what do I get? I'll get e to the 0, which is 1, and e to the 1. If I get theta equal pi, that's still a 1, but that is e to the negative 1. And I go to theta equal 2 pi, I'll notice I'm repeating. And I'll tell you what that means. I'm going to give you the graph of this function. If I want to know where does dx dt equal 0, that would indicate I'm looking for a vertical tangent. And that's when cosine of theta e to the sine of theta equals 0. That's either when cosine of theta equals 0 or e to the sine of theta equals 0. That's impossible. Exponentials can never be 0. Where does cosine equal 0? That happens when theta equal pi over 2 plus pi k. So that's going to happen theta equal pi over 2. In this case, I'm going back to the traditional. E to the 1 is e1. Theta equal 3 pi over 2. E to the negative 1, 1. And I noticed that theta equal 5 pi over 2. It starts repeating. So those don't count, but I'll show you what they mean in a minute. I sketched the graph of that on my graphing calculator, and I found out that this is what the graph looked like. So theta equals 0. I am at 1e1. There's 1. 2.71 is right there. You have a horizontal tangent. Excuse me. And at theta equal pi, I am at 1. 1 over e is right there. Also, I have a vertical tangent at theta equal pi over 2. I am at 2.7, 1, 2, 3, 2.71, I'm right there. And at 1 over 2.71 right there. And there it is. And of course those repeat because if you run a motion, you're going to get through those points an infinite amount of times. But what does that mean? That's for your next class. You can't have all the fun in one class. You must have something safe for 5C. 5C is where you put everything together. You know, that's where all the fun is. I'm going to go back and reinforce something that we learned, but now you're going to do things the easy way. If y is some function of t, and x is some function of t, then if we understood section 8.1, then ds is the square root of dx dt squared plus dy dt squared dt, which indicates I no longer have to worry about should I do this with respect to x or to y. If you look at the derivation I did in section 8.1, And instead of dividing, remember that? I could derive it here, but you know, if I divide by dt squared and do the work, I will end up with this. L equal the integral of ds, where ds in this case, it's not two cases, it's a single case. It always depends on t. And add to that, if I want to find the surface of revolution about the y-axis, I'll say surface is the integral of 2 pi about the yx ds. Wouldn't that be the integral 2 pi, assuming somehow that x is between a and b, so from a to b, and wouldn't that be, in this case, isn't that always fixed, and I don't have to worry about whether I should change it or not? And ds, isn't ds the same no matter what? And how come we didn't do that from the beginning? Well, we didn't really apply parametric yet. How about the x-axis? Well, I know s is going to equal the integral of 2 pi y ds. Well, hey, that's the integral from a to b with respect to t, 2 pi, the square root, literally what you see right there. The only difference is that I know what dx is, and dx is simply f of t. So no need to worry about, well, should I do this in terms of x or y? You can do it in terms of t, and everything's going to match. That makes this very simple. And again, in 5C, you're going to really apply this heavily when you write those as vectors. I'd like to do 2 more problems. 38. Set up an integral that represents the length. L equal the integral of ds. Normally, I have to worry whether I'm going to do this with respect to x or y. In this case, that's simply the square root of dx dt squared, dy dt squared, dt. T runs from 1 to 4. What is dx dt? 2t minus 1. What's dy dt? 4t cubed. And guess what? There it is. Isn't that just amazing? Just like that. And what if I wanted to find or set up an integral to find the surface obtained by rotating the curve about the x-axis? The integral of 2 pi y ds. And let's see how challenging this is. 2 pi, it's with respect to t. T equals 0 to pi over 2. And y, before I even begin, I know that y is the sine of 2t. And dx dt squared plus dy dt squared. And there it is. That's simple. And what if I decided to change the order on those? Well, hey, guess what? Then s is going to equal the integral of 2 pi x ds. Well, in this case, again, 2 pi is a constant. And how does that work? Well, I know what x is. I don't even have to worry about that. That is e to the t minus 1 minus t. I'm going to put this underneath so it fits with these. So I don't know. Come on. Wasting time here. There we go. My s's look like 5s, so that's why I always put that extra. And what would this be? dx dt squared, dy dt squared, dt. What's dx dt squared? E to the t minus 1. What's dy dt squared? Bring the power down, 2e to the t over 2. And there it is. And we're done. I'm going to give you the homework in this section. Be careful, there's an added bonus in the homework. And there's the homework. I'd like you to work out 10.3. 2 and 10.3, I wanted to do those two problems. They're a lot more important than you think. And that would be it.